Good evening, everybody, and welcome to our Razoom, this first one in the new year. I'll try and keep my comments short because you don't want to sit listening to me rabbiting on. Tonight we have Alex, who's been doing a lot of work with fast radio bursts. So we'll be handing over to him very soon. And next week we have next month, sorry, we have our oh yeah, my brain has gone. I expect you already know. Just get my yes, it is. It's meteor. We have an evening on meteor observations from the IMO next month. Something to look forward to. Anyway, this evening it's Alex, and I'm just Alex is a PhD student, so we welcome you, Alex, along with all our friends from the USA. I see a few have logged in this evening. Always good for you to join us from Sahara. Alex, it's over to you. As I say every month, our screens are yours.
Great, thanks for having me. Okay. Everybody can see my screen and hear me okay?
Yeah.
Great. Yeah, well, again, thanks for having me. This is a great opportunity. Today I'm going to be talking about Frbs, fast radio bursts, CHIME, and some of our discoveries. I think just as a sort of upfront, I want to do sort of a high level or broad overview of all these subjects. There's a lot to go into, but I'll try to be brief and sort of keep it minimal. So I think to start with, the section will be just going over some of the historical context. Fast radio bursts are relatively new, but there's a kind of rich history leading up to their discovery, and through exploring that, I hope we can sort of see some of the main key observables, what a fast radio burst actually looks like, what can you learn from, what kind of information is embedded in these pulses. And from there, we'll go on to more of a technical overview of the CHIME instrument. I'll talk a little bit about its origins as a cosmology experiment, and then go through the hardware and talk a bit about our own pipeline running on this instrument that is looking for fast radio bursts pretty much 24/7. And then finally, I'll just go through all of our discoveries that we've been putting together over the last few years of operation now. So to start with, the story of fast radio bursts really, I think, is really rooted in pulsars and pulsar astronomy. A lot of our observational techniques today is really, it just comes from this rich field of pulsar astronomy. So this all started in 1967 with Jocelyn Bell Burnell's discovery of the first pulsar. Here at the bottom, we see these pulses, these regular pulses she's observed. So what is a pulsar? It's a neutron star rotating. We have a magnetic axis and a rotation axis, and if they're not aligned, you see this beam sort of sweeping your line of sight. And so the really high magnetic fields of these neutron stars, which are the remnants of large stars after they've gone supernova, to sort of 10 to 25 solar mass range. And these remnants are very compact, about solar mass, 10 kilometers across for radius. And like I said, very high magnetic fields, which accelerate these charged particles and give us these pulsed emissions that we're seeing. These are really interesting objects for studying things like general relativity. They're very high mass, high gravity situations. And since their discovery, they've given us really a wealth of knowledge. Within the sort of class of these spinning neutron stars, we have lots of subclasses. And over the 50 years that these things have been discovered, a lot of these subclasses have emerged and sort of motivated the way that we search for these things. We have giant pulse emitters, like, well, showing here the crab. This is an image from Chandra in X-ray. Giant pulse emitters, these are, you know, nanosecond scale pulses of higher fluence. We have interesting binary systems like the one discovered by Halston Taylor in the early 70s, I believe, which was used as the first evidence for gravity waves. You can see as the neutron stars orbit each other, the decay of their orbit following Einstein's theory of general relativity. Also in the 70s, we have the emergence of millisecond pulsars. So these are neutron stars that are spinning, you know, on a millisecond time scale. These have been recycled by accreting material from a binary to spin them up. And these are some of the most like stable clocks in the universe. You can use them for all kinds of interesting timing science. For example, detecting stochastic background of these supermassive black holes coalescing. So they're really great tools for gravity wave science. We also have nullers and mode changers. These are sources that have, you know, sort of, as they pulse, they turn on and off, and their profile and pulse changes. And these are sort of mysterious objects in their own right. We also have magnetars. These are very young neutron stars, and we have a big population of sort of the typical rotation-powered pulsar. These magnetars, there's about 30, and these are even that much more extreme in their magnetic environment, something like 1,000 times a normal pulsar. We also have rotating radio transients, or RATs, and these are sources that just emit very, very sporadically. You do see a pulse period, or these pulses are arriving at some spin period, but it's not constant. And these rotating radio transients, I think, are probably the most important connection to fast radio bursts, just in their way of detection. A lot of these other systems I've listed here, the typical way you'll find them is by leveraging their periodicity. So you'll search in the frequency domain, or you'll do stacked observations where you're folding around this potential period. But rotating radio transients, the best bet to find those is just in their single pulses. And so while the first few pulsars were detected through single pulses, for a long time, it was all periodicity. So in 2007, we have the first discovery of a fast radio burst. And this is discovered through single pulse. This is sort of what it looks like, or this is what it looks like on the right here. Our data is typically channelized in frequencies. So that's the y-axis here. And then sampled in time, just the x-axis. So the sort of characteristic feature, and probably the most important observable, is this delay you see, with the high frequencies arriving before their lower frequencies. When this pulse was emitted, everything was at the same time, but as it propagates through space, since it's not a vacuum, these free electrons are causing, it's basically a refractive effect, where the index of refraction is frequency dependent, and you get the different speed for the different frequencies. The time delay here, it scales as the frequency to the -2 power, and that's a really key observational signature. It really helps us determine whether something's actually astrophysical, or if it deviates from that, maybe it's more likely to be terrestrial. The other thing it scales by is this DM, or the dispersion measure, and that's the integrated along the line of sight from us to the source. It's integrated electron density, free electron density. So in some ways, this dispersion or this amount of delay it's a proxy for distance. It's telling us how much material this pulse has traversed. With models of our galactic electron distributions, we can have some expectation, given some line of sight, how much electrons we expect, and therefore how much of a delay we should see. Now this pulse, well, in a lot of ways is very similar to a bright pulsar pulse. What's exciting and different about it is just the amount of this sweep. Is much more than what's expected along that line of sight, which was at this time looking out to I think the Large Magellanic Cloud. So it couldn't be explained by any galactic contribution, and so it had to be extragalactic. If it was real, there was nothing in that region that could really explain it. And if this was the case, it would have to be something much, much more energetic than a typical pulsar pulse. This itself was quite bright, something like 30 Janskys. But with the distances inferred by this large sweep, we're starting to look at energy in excess of something like 10 orders of magnitude of what you'd expect from a galactic pulsar. So this is really unexpected and really exciting. It wasn't until 2013, however, until more of these extragalactic pulses were seen. Again, this was seen from the Parkes Observatory in Australia. And I just want to, I guess, bring a second observational feature to your attention now, which is this scattering. As you see in this inset in the upper right here, the pulse profile is narrower at higher frequencies and progressively gets larger for lower frequencies. And you see this one-sided scattering tail, this exponential fall off. What this is due to is a multi-path propagation effect. As the pulse propagates through maybe clumpy or turbulent medium, it's gonna scatter, and you're gonna get certain lines of sight. So this tail, these are lines of sight that have effectively reflected off this material and come back to our line of sight. And this is a very strong frequency scaling. It's the time scale here scales with frequency to the 4th power. Now, this is a powerful tool, though, for probing the sort of the geometries and the environments around the hosts of these objects, as well as what they're passing through. So with this sample, it's actually 4 bursts. The field is really kind of solidified. The term fast radio burst was coined, and things started to ramp up a little bit. Still in this era, though, it's sort of 1 or 2 bursts a year. We have the first non-Parkes detection here with the Green Bank Observatory in West Virginia. And this was good because there were still some doubts that maybe there was some instrumental effect going on, maybe something with the pipeline or some bugs. But this really solidified that it was this extragalactic source class and nothing instrumental going on here. In this burst, we see 1 more signature, which is related to scattering, and it's a scintillation, where we don't just get a delay giving us the scattering tail, we actually get an interference pattern. So you see in this inset, we have a growing and fading of the intensity as it interferes with itself. This was an interesting source because it really, through modeling the scattering tail with this scintillation, you could deduce that there's actually 2 screens going on, one for the Milky Way and one closer to the source, which indicated that the source was maybe embedded in some dense magnetized plasma, something turbulent, and giving us the second source of scattering that we wouldn't maybe expect. Up until this point, though, it's just single one-off bursts. A lot of these spots in the sky are followed up for many, many hours at this point, but nothing has been seen to repeat again. A lot of the models, given the extreme energies, are invoking a cataclysmic event, maybe inspiring neutron stars coalescing or some extreme supernova situation. There's also a lot of exotic theories going around at this point, invoking things like cosmic strings or white holes, black holes. It's really a zoo of theories with not many observations right now. In 2016, this changes quite a bit, though. We have the detection of the first repeating source of FRBs. We can either have multiple source classes at this point, or we need to at least cover a non-cataclysmic scenario. At this point, we're starting to really suspect magnetars for their energetics or neutron stars, not only for their similarity observationally, but now we have repetition. But there's still the question, do all FRBs repeat? What's going on here? There's a really important lesson, I think, from the GRB field where things really diverged into long and short GRBs, and it took some time and some statistics to build that up. This source really, over the next few years, continued to give a lot of milestones and exciting information. We have, given that it's repeating and we know where it is on the sky, we follow it up with interferometric observatories like the Very Large Array, as well as the EVN, and it's localized to a small dwarf galaxy at a redshift of about 0.2. This dwarf galaxy turns out to be quite low metallicity and is star forming as well. The EVN work gets us, I believe, milli-arc-second resolution, and you can actually see within the dwarf galaxy a bit of an offset. And this FRB is further associated with a persistent radio source. At this point, still, it's a question of how canonical could we treat this? Is this what's special about a dwarf galaxy? What's special about the low metallicity, the star forming? What kind of clues and how much can we really lean on this? And now in 2018, we have a really interesting observation of this source. This is at higher frequencies than maybe what I've shown before. And we see a really interesting effect here. So observationally, this is rotation measure. So as you have linearly polarized light propagating, if there's any magnetic field, that parallel component of it is going to cause your a rotation of your polarization angle. And that rotation is going to be wavelength dependent as well. It scales with the square of the wavelength. This rotation measure is very similar to the form of the dispersion measure. It just has this term for the magnetic parallel magnetic field. And what we've seen from this is, well, what I'm showing here is the frequency as well as the Stokes U and Q parameters, showing the linear components and the different orientations as a function of the total linear. So with this rotation measure changing as a function of wavelength, you see these different components oscillating, and you see the stretched out effect, which follows from the lambda squared here. The rotation measure value here is very, very high. So 10⁵ radians per meter squared. For pulsars and other sort of extragalactic sources, typical values are 10s to 100. The only other sort of comparable high rotation measure is the galactic center magnetar. What this rotation measure tells us is that this source is embedded in a environment that is highly magnetized. And this is another very, very important clue. This polarization information is something that's difficult to work with and is not always available, but it's very powerful. Can sort of probe the environments as well as the emission regions with things like polarization angle swings. It's a technique that's been pioneered in pulsar astronomy as well. So a year later, we have higher resolution data, more quality data on this source, and we see an interesting emergence of just very structured pulses. This is not what we saw with the first few one-off sources where they were quite broadband, quite simple. There's always the question of how much of that detail you're resolving. Is your sampling rate sufficient? Maybe these things are complex, but you're just not resolving them. But nevertheless, the sort of straightforward picture here is that these are quite more complex than what we've seen before. One feature we see is these marching down substructures where these subpulses are getting smaller or decreasing in frequency as time goes on. This is deemed like the sad trombone effect. Womp, womp, womp. But this is another clue that will be very important to theorists as they try to imagine scenarios that can explain this, as well as the energetics, as well as the other features we're seeing. So just to summarize some of these key observables that we're looking at, we have DM, dispersion measure, and this is a frequency-dependent delay. Turns out to be an incredibly useful tool. It's a proxy for distance and will help us determine things from terrestrial versus astrophysical, and combined with models of our galactic electron distribution, we can use it as a tool to determine whether something is extragalactic or more local. We have scattering and scintillation, which will tell us something about the environment and the intervening material. However, these effects scale very strongly with frequency and can impose a very, very strong selection effect for low frequency telescopes. We have polarization and rotation measure, which can tell us things about the magnetic fields and as well as the emission region geometry. There's some other things I haven't listed here. We can measure the drift rate of these subpulses. We want to be measuring the widths and the energetics and whatnot. But here's a sort of the spectral features we're looking at to characterize these bursts, and that allow us to use them as probes. Okay, so I'll stop the sort of lead up to CHIME. This is the picture before CHIME comes online. We have, at this point, maybe a couple dozen fast radio bursts. We have one repeater. We don't know whether they're the same class or not. We know that we haven't seen anything remotely as energetic in our own galaxy at this point. And we have still lots of theories, and we really need more data though. Couple dozen, we're sort of seeing 1 or 2 a year. And this isn't a lot, but given the fields of view of the telescopes looking for these fast radio bursts at this point, we can actually infer a relatively high sky rate of maybe something like 1,000 per sky per day. It's just we need bigger field of view instruments. We need more dedicated searches. we need more compute power, and that's what CHIME is going to do for us. So CHIME, it stands for the Canadian Hydrogen Intensity Mapping Experiment. And this instrument was originally devised to answer a cosmology question. The goal is to measure the expansion rate of the universe over a very specific window of time. So a redshift range of 0.8 to 2.5. The way it's going to do this is by mapping large-scale structure by looking at the neutral hydrogen, well, redshifted hydrogen 21 centimeter line. And the sort of the cosmological observable here are baryonic acoustic oscillations. These are really interesting, really cool tools where overdensities in the very, very early universe, which propagate and expand as these characteristic shells, will get frozen out at the time of recombination when the CMB is emitted. And they impart this characteristic structure of overdensities, and those persist from the very, very early universe all the way to the present day. And you're more likely to have galaxies clustered apart from this on this characteristic scale. And this makes it a standard ruler. You can track this characteristic length scale throughout the history of the universe to track the expansion of the universe. Now, previously, most surveys to do this sort of work, they do it by looking at the galaxies as individual objects and getting their positions and redshifts, and that's not what CHIME is doing. CHIME is not resolving individual galaxies. It's just resolving this characteristic scale. So you can think of it as a bit of a blurring out of the large scale structure and just getting at that characteristic scale. It's a really hard problem because here the galactic foreground is a big problem, and it's about 10 to the 5 times brighter than the large scale structure that we're looking at. This takes a long time, and to integrate to get your images, but more than anything, you really need to have a well-characterized telescope and instrument. Really need to understand the beam. So I'll take you to CHIME now. This is it's located at Penticton, British Columbia, so South BC. Here's a satellite view of the observatory that it's located at. This is the Dominion Radio Astrophysical Observatory. We have the 26-meter John A. Galt telescope here, which was involved in the very first very large baseline interferometry, linking up with observatory in Ontario. We have the 7-element synthesis array, which is involved in the Canadian Galactic Plane Survey. We have the CHIME Pathfinder, which is a test bed for the CHIME instrument. And we also can see this large T-shaped array. This is from the 60s. It's a 22 megahertz dipole array. The observatory also houses a solar monitor, which has been monitoring the sun for decades at this point. So this is what CHIME looks like. It's constructed from 4 20-meter wide cylinders, each 100 meters long. And along the focal lines of each cylinder is 256 dual polarization feeds. So it's an interferometer. It's no moving parts. It's a transit telescope, so it focuses just in the east-west direction and will map the sky just as the Earth turns. So it's ideal for map making. It's essentially horizon to horizon. There's some shielding mountains all around it, which makes this a good observatory spot. Yeah, it sees roughly 3 pi steradian per day, very, very high mapping speed. I'll just go over the system block diagram here. So we have the feeds, or the cylinders, and we have the feeds coming in. It's the correlators in FX design. So that means just that the channelization from the feeds is happening before the spatial correlation. So the channelization is handled by the FPGAs, while the X engine is a GPU correlator. The data rates here are quite insane. At its widest point, this telescope is processing about 13 terabytes per second. I'll just go through the analog signal chain now. Here are the feeds. They're just printed circuit board, so it's really cheap to make. Everything feed-wise, we want to be as cheap as possible because you have to repeat it 1,000 or 2,000 times and need it to be compact as well. So these are the pedal boards. Here's just a simulation of the current response for an east-west polarized wave. From there, we go to the low noise amplifiers and the filter amplifiers. The filter amplifiers are defining our 400 to 800 megahertz bandwidth. And these are all quite small as well and cheap, really thanks to the telecommunications industry. A lot of this telescope wouldn't really be possible too long ago in the past, but it really relies on a lot of hardware, consumer hardware, or consumer level hardware. Here's just a view of the FLAs as they come in. This is in a RF shielded chamber, and these cables are connecting over to the analog to digital converter. So I had the pleasure of screwing in all of these feeds for half of the telescope. It's interesting, but it is a lot of cable. Altogether, it's over 100 kilometers of coax cable. So it's quite the task, especially this 50-meter cable going from the feeds down to these RF sealed shipping containers. The F engine, where the channelization happens, is performed on these custom-made ice boards. So these are developed at McGill, and it's an FPGA-based setup where we have a polyphase filter bank and an FFT, which does the channelization. It's sampling at 800 million samples per second and is producing an output of 1,024 frequencies at a time resolution of 2.56 microseconds. After it does the channelization, it needs to do a transpose before the different frequencies can be spatially correlated independently of the different frequencies. So between the end stage of the channelization to the processing and the X engine, we have this big transpose. Now the X engine is also housed in the shipping containers. Now these ones are full length, and there's 2 of them. And it's GPU based. I believe there's 256 GPUs or 256 nodes, but I forget. But this is what it looks like inside. They're all water cooled. And here's all the fiber which connects to the FPGAs. So as it's a digital instrument, we have this really great opportunity to sort of split off the data streams. So there's actually 3 projects that are active right now on the CHIME telescope. We have the original cosmology instrument, which is doing these 10-second long integrations, 124 frequency bins or redshift bins, and it's doing a full n-squared cross correlation for image making. So that results to about 2 million visibilities. Chime Frb, on the other hand, is looking for very fast things. Fast radio bursts are typically about a millisecond. We need higher frequency resolution because we want to mitigate that dispersion smearing as you go from one channel to the next. We want to correct that as best as we can. So the correlator for us is producing 1,024 static beams on the sky. It's a grid of 4 east-west and 256 north-south. Each of these beams will be searched independently, and the results will be collated as we find bursts in real time. The last backend here is a Pulsar Tracking machine. So it's producing a much higher time resolution, but smaller frequency resolution. And it's giving full polarization information to 10 tracking beams, which can be assigned and switched effectively instantly. These pulsar beams are used for things like FRB follow-up, just daily monitoring of pulsars, and it's really useful for monitoring timing variations, which are really important for these millisecond pulsar timing arrays. So the FRB engine is its own CCAN, full length again, but this time it's CPU based. So we have 128 nodes. Each processes 8 of these static beams. The sort of rough process is a long chain of RFI excision. We have a lot of RFI problems. We see cell phones, TV channels, planes, satellites. So we have a decent amount of compute just dedicated to clipping, detrending, just trying to find outliers without removing too much of the data. Then the next big part is this dedispersion process. So correcting that frequency dependent delay. And we need to do this for tens of thousands of DM trials. It's a blind search. We don't know how far away a given source might be. So we have to try all these trials of dispersion measures. From there, after you've corrected and shifted the channels, we want to find quick peaks or pulses. And then from there, it's really sifting through all these candidates, grouping them together, extracting different metrics on all these candidates that are streaming through to make decisions. Is this actually astrophysical? Is it more likely to be a plane? Maybe the whole array of beams is lighting up. So we use some machine learning techniques there. But altogether, this is a real-time process, and we're trying to make a decision as quickly as possible. Our nominal sort of latency right now is 10 seconds from when the burst just leaves our band to when we can make a trigger to save some data. We have the opportunity to save intensity data as well as this higher resolution baseband data, which has the full polarization information to do things like the rotation measure or polarization fraction. Another big thing that we want to do, and we're kind of on the cusp of having running smoothly, is the opportunity to broadcast our good quality events and alert the community immediately. So other telescopes can perform their own follow-up on interesting events. Here's just a table I'll leave up quickly that shows sort of the most relevant parameters for the Chime instrument for searching for FRBs. Notice our field of view here is quite large. And so we're looking at a lot of the sky instantaneously. For a given source, our beams are static. So a source will just drift through and we can get roughly 5 to 10 minutes at a time. Now, just quickly, I'll go through our key results over the last few years now. We had our first light in summer of 2018. And from there, we entered a pre-commissioning phase, just trying to understand our instrument, calibrate it, understand, are we aligned? Are we detecting things as efficiently as possible? Are we getting rid of RFI? So we went through this long process. But nevertheless, in our first few weeks of operation, we did detect 13 new fast radio bursts. And within that sample, we found the second repeating source. From there, we continued in the theme of detecting existing and new fast radio bursts, repeating sources. So we've seen the original repeater actually just once. So from the context of CHIME, it's not a repeater, but we didn't really expect to see it. It's not a bright source, and CHIME is not the most sensitive, but we did see this one bright one. It's quite smudgy. We think there's probably unresolved substructure here that drifts down. We can also see another characteristic of these repeating bursts seems to be not this broadband features, but we're starting to see these sort of Gaussian islands of emission. From there, we just keep expanding the population of repeaters, and we publish first a sample of 8 and then 9. Here's just showing these postage stamps of the emission. The different colors are the different sources. And here again, this is a next set of 9, and these are showing our best guesses for the positions. Now at this point, our localization capabilities aren't that good. You see a lot of these are actually quite big in size. And this is sort of the size of our main lobe. So these are our side lobes. And it's hard in some cases, especially with these narrow band bursts, to rule out just from the beam detection information whether it came from a side lobe or the main lobe. And so at this point, we're being quite conservative with our uncertainty regions, just hopefully getting a good enough so people can do effective follow-up. These positions will improve and are improving as we move towards getting positions out of the baseband data. This has just been a long process of calibrating our techniques and trusting our error bars. And then just recently, we found a really interesting repeating source. This is very, very close. It's only 4 megaparsecs away. This is associated with the M81 galaxy. So it's just off the main bulge. This is our initial uncertainty region. And the source 3 is where this repeater ended up to be. And this is really interesting because not only is it close enough to allow for potential X-ray follow-up, but just the environment it ended up being in is a globular cluster, which you wouldn't actually expect for a lot of these young theorized sources, magnetars, young neutron stars. So as we see these associations growing, not only with CHIME, but with other telescopes, such as like the Australian Square Kilometre Array Pathfinder, ASCAP, localizing FRBs to a myriad of different galaxy types and environments. So the picture really kind of is becoming more and more interesting, I would say, and less clear as more sources are found. We also found a repeater with a 16-day activity cycle. So it wouldn't be like a rotation cycle where you're getting one pulse every 16 days, but rather a window of heightened activity. Other telescopes have looked at the source and found a similar thing with the window shifting in frequency. This source is also being localized. That's home to a spiral galaxy, I think about 150 megaparsecs away. So this 16-day cycle, it smells kind of like a orbital period. But the significance of that is still unclear. After we reported this, there's also some tenuous claims of a really long orbit in the original repeater, something like over 100 days or something. So could be another clue. More recently, we found a periodicity on a different time scale. This is within one train of pulses. We have one that's very solid. I think this is roughly a 6 sigma detection. Whereas these, they look convincing, but we've run a large number of simulations saying if you have 5 pulses and you randomly distribute them, how often do you get something within this tolerance? So this is maybe a 2 sigma, and I forget what this is, but we do have one clear case where we can claim periodicity in a sub-second time frame. This smells like a rotation period. 1 second is typical for a pulsar. Magnetars do tend to have longer periods as compared to some of the other pulsar populations. This is a really exciting clue as well. Now, a big thing we've been working on the last few years is just publishing everything we've seen. So we released our first catalog, and it's not a complete everything we've seen, but it's the first year of our operations. So it's 536 new Frbs, up from roughly 100 by the time we had, or 60, I believe. So it's a huge increase in the population. And importantly, this is a big sample from one telescope. So it's uniform detection biases, uniform selection function. And this really opens up the door to do more statistical studies rather than looking at one-off interesting sources. So some just broad overlines from our catalog, we're finding that the distribution of energies is consistent with a non-evolving population, non-evolving in redshift. So this is an isotropic uniform distribution. We're not favoring nearby sources. We're not favoring highly cosmological sources. We're also finding a rate of roughly 800 per sky per day, and that's above a fluence of 5 Jansky milliseconds. One thing we did a lot of work to do is just characterize our selection function. It's really important to know what we're not seeing before we can say something about what we are seeing. So we've done this very large scale injection campaign where we're simulating pulses and adding them to our live system and seeing which we detect and which we don't detect. This tells us our biases along different parameters such as dispersion amount or pulse width or amount of scattering. The corrected distributions are interesting in that we find a really large population or a potential for a large population of highly scattered bursts that we're not missing. or we are missing. We've also looked a bit more in depth at the spatial distribution of these sources. We want to see, is our galaxy imparting any selection bias or detection bias? Is our sensitivity of our telescope? Do we understand these things? Are we detecting FRBs where we ought to be? And the answer is yes. I think probably the most interesting avenue of this, having this big sample, has been to sort of get at that question of one-off events versus repeater bursts. And this is really interesting, where we are seeing a true statistical difference in the bandwidth and the duration. So it's less likely that one-offs are just repeaters that have a low repeat rate and aren't seen often, and maybe eventually are truly a distinct population. We're also able to do some true like cosmology with this now, and looking at cross correlations with galaxy catalogs, and we're seeing a cross correlation that's significant in a redshift range of 0.3 to 0.5. And through these correlations, we're also finding potential for a population with a large host DM. So sources that are embedded in dense or extreme environments seem to be present. We've also looked at trying to recreate the width and DM distribution using these Monte Carlo simulations, where we start with different populations that are distributed differently in our galaxy, maybe according to some models, perhaps tracking star formation or tracking how pulsars are distributed in other galaxies. We're finding it really hard to recreate the scattering if we just use our own galactic pulsars as an analog. It seems like these events are truly coming from environments that are more extreme. The most sort of agreeable normal situation has our FRBs spatially distributed, not like pulsars, but like short gamma ray bursts, as they are in spiral galaxies. And finally, I'll just say we sort of have a bit of a smoking gun now of what these things are really coming from. So in 2020, we detected this magnetar, this galactic magnetar. It was also detected in X-rays, and we weren't the only observatory to detect it. We were quite off axis, but it was still incredibly bright, lit up tens of beams. And we saw it in our CHIME, as well as the telescope we're building in Ontario for very long baseline interferometry. This is sort of bridging the gap in energy between galactic pulsars and very energetic FRBs, although there's still orders of magnitude spread. This truly was, though, a new scale of observation for a magnetar burst. This is 3 orders of magnitude brighter than any previously seen burst. So this could be the connection that we've been waiting for. So just to summarize, the field of fast radio bursts is really in motion. It's quickly evolving. CHIME is really right now at the center of things. It's really exciting. We have magnetars seeming like a probable progenitor, but we don't really know if there's multiple source classes, what's going on. It's a field that's being driven through individual interesting discoveries, as well as a statistical approach, and it'll continue to be this way. And FRBs as cosmological probes are exciting. I didn't finish that, but that was an area that I'm personally very excited for in the future of fast radio bursts. Okay, so with that, I I'm done, and I will take any questions.
Alex, thank you so much. That was just astonishing. Fantastic. Yeah, there may well be some questions. We've got some time. If you do have a question, please ask Alex now.
Maybe I can start if you allow, Paul.
Please.
One of the things I'm particularly interested is the idea of the progenitor, or the question of Magnetars progenitors. One of the characteristics that you see in repeat fast radio bursts is the hadron-Bohm effect. And the thing is that with this galactic magnetar that you have observed, you see something like an inverse hadron-Bohm. So let's call it a happy trombone. My question would be, if you look at one-off events, one-off FRBs, have you seen any hadron-Bohm effects in one-offs?
Yes, yeah, and we've even in a few cases seen this sad trombone and then predicted that it would repeat, and lo and behold, it has. So it seems to be a very good predictor. We have a few cases still in the catalog of showing this drifting, showing this wide, and we haven't seen the repeat, but people will be following up and giving special attention to these. Yeah.
Yeah. Another characteristic that you have pointed out is that doing the difference between the repeaters and the one-offs is the spectral characteristics. So the repeaters seem to be more spectrally confined. Again, is that something that has been consistent through all the various samples of one-offs and repeaters?
I would say not exactly. So the first repeater, for instance, a lot of its first observations were quite broadband, and it didn't seem to be later until we had these more localized things. And one thing to point out there, I think, is there's a lot of observational biases against detecting these more narrow, broad, spectrally confined bursts. So we're sort of needing to tune our search algorithms as well to be more sensitive to non-broadband bursts. Another thing we struggle with ourselves is disentangling the beam effects from what's intrinsic. Our side lobes are quite sensitive, and they sort of impose like this 50 megahertz or so bandpass. So that's very, very difficult to disentangle. Actually, okay. Even in this example with the magnetar, we see these hotspots in the spectrum. This is actually just a beam effect.
No, it's not scintillation. It's a beam effect. Yeah.
Yeah.
Maybe a final question on this particular magnetar. As far as I recall, there have been a number of subsequent observations, and there have been pulses seen from this magnetar, albeit with a much lower intensity, sort of in let's say in the normal range of what you would expect. Has there been characteristics like the hadron-Bohm in those lower intensities observations as well?
I'm not exactly sure. I haven't been following this source as closely as. So yeah, sorry, I can't answer that.
Can I have a question? I was just following the dates as you were describing when FRBs were being discovered and when CHIME was coming online. I'm going to guess that CHIME wasn't designed specifically for FRBs. So was there a sudden sort of redesign process just before you sort of turned it on and came online?
A little bit, yeah. I'm not sure what time in the design process, but they did sort of catch on early that it would be an amazing instrument to find FRBs. So while it was being constructed or planned, there was additional grants put in, and through the money being allocated for the FRB system, the correlator got an upgrade. So the design did change a little bit, but all the fundamental aspects are driven by the cosmology needs. So the baseline size, the antenna spacing, the frequency range, those are all cosmology. But the instrument did receive additional funding with the FRB project.
So it was this ability to strip off those 3 data streams that was the redesign. It was all in the digital domain.
Yeah. Yeah, to accommodate that, the GPUs were upgraded basically.
Niks.
I'll have another question if it's all gone silent.
Yeah, go ahead.
Sort of again back to the historical story. Once FRBs were identified, was there a huge effort to sort of mine back through old data to see if they were there but had been missed because no one was looking?
Yeah. So even the first one was from archival data from 2004, and through this high time resolution survey, I forget the complete acronym, but I think a lot of this old data was sifted through. I don't know of any main archival ones that came out.
If I recall correctly, the first repeater was also seen in archival data.
Okay.
So never throw anything away.
Yeah.
I have a question.
Go ahead.
Oh, I'm sorry. Go ahead.
Oh no.
Could the non-repeating single burst FRBs be due to some type of micro-lensing effect of another object that's being amplified and then appears as a pulse by some type of a gravitational focusing effect?
Yeah, that's a great question. We're certainly looking for these lensing events in our own data, but more through the context of a pulsed emission, a pulsed emission being lensed, giving 2 copies of that, so you can cross-correlate the signals and try to deduce that. But as far as a persistent source that was crossed by a gravitational, I don't think so, but I'm not sure.
May I ask a question, please, Alex?
Sure.
Let me just take these off. The frequencies that are used to measure these range from the mid gigahertz to 2 gigahertz down to your 400 megahertz. Is there an optimum frequency for observing these?
Yeah, so since CHIME came online, there's been some lower frequency detections. So LOFAR in the Netherlands has detected around 150 megahertz, and they have gone as high as I believe 9 or 10 gigahertz. So the frequency, it does matter depending on what you're trying to do. So certain scintillation effects, you'll want to be at a certain wavelength. I believe the rotation measure the high rotation measure was really required to be in the gigahertz range. On the other hand, so pulsars tend to have a power law spectra that grows or increases with lowering frequency. So from that perspective, there are some arguments that lower frequency is good. There's also just the field of view increase you get from going low frequency. But then of course you're can be struggling with scattering or even absorption as you go down. So that's sort of the fight. I think the optimum is just going as wide as possible and having, if possible, multiple wave bands shadowing each other.
Yeah, okay, thank you very much.
Is that, just to follow up about the bandwidth of these things, is it limited to the radio band, or are they detectable right across the spectrum?
Yeah, as apart from the coincident X-ray detection, there's been a lot of efforts to also detect in X-rays. So in the pulsar and magnetar world, you typically will constrain yourself to radio or X-rays, although there are optical detections of, say, the crab. But as soon as you get like different absorption effects, radio is really your best bet for anything distant. But yeah, there has been lots of efforts to detect these in all wavelengths, and a lot of telescope time, I think, has been spent staring at these repeating sources.
To no avail by the sound of it.
Yeah, to no avail.
Do we have any more questions for Alex?
But perhaps just a quick one. Looking at what you called the cylinders for CHIME, are they in fact circular cylinders or are they parabolic?
Parabolic.
Yeah.
Yeah.
Okay, thank you.
Yeah, and I believe the focal length is 5 meters. And the mesh is basically chosen to let snow through. Yeah.
I do have a question. You can pick up the interstellar medium densities with your dispersion measure. Has there been any correlation of what we know about interstellar medium now? I mean, intergalactic medium, I should say.
Oh, yeah, so yeah, I'm just trying to recall, there's some work using fast radio bursts to constrain the ionization fraction. I forget where that stands. There's also been some work following our catalog, seeing increased dispersion measure with sightlines associated with like nearby galaxy clusters. And a very, I guess, useful, maybe just a use for FRBs is to try to map the halo densities. So that's something that's really unconstrained. I think estimates for our own Milky Way halo is something like 20 to 50 DM units of additional dispersion just from the halo. But as we get more sources, we'll be really mapping that out. But that's ongoing work, yeah.
Okay, thank you.
And then also as these sources become more numerous, the rotation measures will be useful for mapping out the magnetic field of the IGN.
Do we have any more questions? We've got time, otherwise we'll move on.
Has there been any attempt to correlate some of these observations with LIGO?
Yes, yeah. Also to no avail at this point. But we are sharing our data even before this real-time event sending. We're trying to correlate even subthreshold triggers, but so far, no luck.
Too bad.
Yeah. The same goes for neutrinos.
There is a question on the chat line about whether this is affected by rain or snow.
Yeah, actually, we seem to have rain affecting us the most. The focal lines aren't as waterproof as we would hope, and also just the humidity seems to degrade our calibration. So some days are flagged for just being too poor data, mostly to do with rain. And we monitor the sensitivity daily by with pulsars actually. And the other problem environmentally has been birds nesting. So they really like the focal line. So we have to have no holes more than about a few centimeters for the swallows.
Has there been any impact on your observations from either Starlink or some of the other satellite constellations?
We haven't specifically looked for, say, Starlink transits. Broadly, we have seen a degradation of our band over the 3 or 4 years, mostly to do with additional like 5G related bands coming online. But we haven't looked specifically for satellites. Our biggest signature seems to be planes. They, I think, essentially become a big reflector, and we see a lot of the nearby city. Nice.
You spoke at once of the large Magellanic Cloud and such. Is there a CHIME planned for the southern hemisphere?
There should be, not that I know of. I'm not sure what kind of coverage like full ASCAP will have. I know there's a similar design. I think it's called Hera, and it's a cylindrical design for also mapping large scale structure, but I don't think it has any FRB backend planned. But yeah, it would be great. I think this is a fairly economical design. I think all in it's roughly 20 million. It's been pretty productive so far as an observatory.
I think there's a telescope, I think it's called Molonglo or something similar in Australia, which is also a similar design. And I have seen a few FRBs, but not to that extent as you have.
Yeah, that's right.
There's a question on the chat line. Alex, can you extend the field of view, or is it optimized for the location? That's from Rob Featherstone.
Yeah, we've, I think, sort of dialed in the optimum range for us. We do see a lot more RFI as we go to the horizon, and then east-west we're pretty much fixed by our reflector geometry. The primary upgrade we'll be doing is a couple of outriggers. which will be smaller versions of CHIME, tilted or rotated depending on where they are, to cover the same field of view. So we'll have one to the east and one to the south. And those should be coming online within the next few years, and will give us essentially milliarc second resolution for each burst we detect. So we'll be able to see where within each galaxy, and not just which galaxy these things are coming from.
How far away would those outriggers have to be? You're just doing interferometry and spacing, correct?
Yeah, our first test bed will be only roughly 100 kilometers away, just so it's easier to work on. But eventually, the baselines would be roughly 3,000 kilometers east-west, and I think maybe 2,000 kilometers or 1,000 north-south.
And here I was expecting just the left side of the field or something. No,
Yeah,
quite
this is-
big distances.
Yeah, very long.
Well, Alex, thank you very much for your time. Time you've taken out to prepare for this from your studies. When do you submit your PhD?
Should be end of this year.
Okay,
Fingers crossed. Yeah.
we wish you well, and this is a field that's moving very fast. So perhaps we'll get you back again in a couple of years' time for an update.
That'd be great.
Yep.
Yeah,
Thank you. Thank you very much. Moving on from national exotic facilities for radio astronomy to something I think equally exciting, maybe, but maybe not quite so exotic. We've got two of our members have got some comments to make on geomagnetic experiments. And first of all, Martin Kinder has resurrected some kit that he's been working with. So Martin, perhaps you would like to unmute and share your story.
Yes, thanks, Paul. And hope you can hear me okay. Good evening, everybody. I was just thinking, this is like going back to that last fantastic talk. This is a little bit like going back to the dark ages. And so anyway, for those, there's a few people here who probably remember me from the old days, but I was an early member when the BA RAG was reformed back in the mid-20s. And I was quite involved setting up some of the prototype kit. I moved house 6 months ago, and I'm just about getting myself organised, and I retired 18 months ago, and I really wanted to get back into this. So one of the first things I wanted to do was try and get my magnetometers going. I had two magnetometers, a very old SAM magnetometer, which got flooded out one year and ceased to work, not unexpectedly, and a UK RAA magnetometer, one of the very early prototypes. So I've been working on them really for about the past 4 or 5 weeks, trying to get them both working. And I thought I'd just bring you a little bit of update for those who might be interested. I noticed that the UK RAA now sell the magnetometer as a board or as by itself with no controller. So what I wanted to do was get back and actually start off with using a Raspberry Pi as a controller and Python. Is it possible to share my screen?
Yes, yeah, it should be possible. Please do.
Okay, thanks. So this just pull into this one here, just to share that. Okay, this is what I've did. This is still the original box that I was using back in 2010, 2011, I think it was. And same controller, if you look at the date on it, it's a 2008 magnetometer. But using a Raspberry Pi, and wrongly, I think in hindsight, but it was a quick way of getting going, was to actually put an MCP, which was what it is, 3008 ADC chip, but piggybacked onto the GPIO lines on the very, very early Raspberry Pi. This is a 2008 model Raspberry Pi Model B, one of the very, very first ones, which I had lying around doing absolutely nothing. I put a 64 gig memory card in there, the latest operating system, which amazingly let it still work. I didn't think it would do, but there again, I did. But the mistake I made, I just used the analog output from the board without using the I2C interface. But I wanted something quick and easy to get going. So the I2C interface comes out, bumps onto the ADC there. It all looks a little bit rough, like all these things do, and it's interesting that I've had to mount the Vera board upside down to be able to solder it to the header sockets. It's not soldered to the board; it's on sockets plugged straight in. But amazingly, it works first time straight away without any real problems. And I was running that off a USB charger. The magnetometer was working off of just a bench power supply. And I decided to try and make a universal, and it didn't work. And the reason why it didn't work was because the ADC was drawing about 2 amps on boot up, shuts down to about 500 milliamps during normal use. But while it was booting up, it was doing then shutting down the interfaces because there was insufficient current to drive them. So it went basically quite dead. And so I've got a little 12 volt to 5 volt power converter, or adjustable converter off eBay for the principal of about £2.36. I've actually bought 3 of them, quite little neat things. It gives about 2.5 amps out. And that really is a very simple, cheap solution to getting it from the 12 volt supply coming into the magnetometer out to the Pi. Another downside of the Pi for anyone thinking going down this path is that no matter what his voltage reference is set for, the maximum input voltage on the ADC is 0 to 3.3, not 0 to 5 volts on the output. So there we go. That was one of those things, but I've got to live with that. And but they've got some changes for that coming along, which I'll explain very shortly. So everything was 3D printed, all the glands and so on to get the Ethernet cable through, and then liberal dosing of silicon gunge all over it to make sure it doesn't let any water in, and it stayed dry so far. For those who want this, are welcome to share the code. This is all done in Pi 3, and there's really 2 bits of code here. There's one bit that runs on the Raspberry Pi sat in the magnetometer board, and what I basically did was actually because it's only a 10-bit ADC, I didn't realize how poor that would be, and I was actually getting a lot of noise. I'm just realized I was only showing this one screen. Let me show you just very briefly what the other thing I was looking at. What the effect of that was this, if I can find it. Boom, 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 boom. Here we are. Let's just share that. Can you see the graph?
Yes.
Right. What you're basically saying is a lot of what I could call ADC noise, and this is caused because the voltage was actually not sitting nicely at a nice ADC level. It was actually basically chopping between various levels. It looked very horrible and dirty. So if I just stop sharing that and go back again to what I was showing you before, it's a bit chopped over change. I wasn't really planning to do this tonight. If I go back to my presentation, whereabouts is it? Where's it gone? Sorry about this, folks. I'm just I'm looking on the screen here. Right. I'll go back to screen 2. I think it's on. So let's just try that one. What can you see? So I'm back to the same graph again, aren't I? Sorry about that. I seem to have lost my share. Just hold on. I'm going to go back. And the reason why is setting where the hell has it gone to? Oh, there we are. Sorry, can't see one for trees. Right, back on this again. So what I basically did was put a 10-point integration in. I did a seed on it. So once the seed is ready for start, it loads an array up, a 10-point array up with a seed, and actually then sets a 0 value, and then basically any changes from there are nice and gradual. And the result was that the graph now looks something like that, which is really quite acceptable. These are live graphs. This is yesterday's data and today's. So that's what it's looking like. And the second program sits down and, sorry, I've gone past it. Basically, it sits on the server, does an SFTP connection, and then pulls the data down and then does the processing, generates the graphs and so on. So the Pi sits out in the garden somewhere. It's about 30 meters away from where I'm sat at the moment, fairly quiet part. And then all the sort of graph processing is actually done back on the server itself, and that's where you can actually see back there. It took me a little while to sort out all the graphs and presentation, getting that right, but that was fairly simple and straightforward. And I've got another program that just moves the files around and images so it appears on a website, which isn't live yet. So that's basically what I was doing with the magnetometer, the UK RA one. Now the plan is to now resurrect my old SAM one, but again, not using the SAM controller, but using the Fluxgate magnetometers, 3 of them, XY, Z formats, so BXB, YB, Z, and then feed that data into another Raspberry Pi. And then when that's up and running, I'm going to modify this one just for out of interest sake to run this on I2C, so that I can actually use the command language that was, I think, developed by David Farr, who's on the call, or he was on the call earlier on, to actually do things like read the data off that way, which would be probably far better, and be able to access the things like the gain control and so on. So that's basically where I'm up to with that. And this has been running for a couple of weeks now. I'm quite happy with it. So if anybody wants to play with this and like the software, I'm very more than happy to share it and talk through what I did. Some other time I'll tell you about the nightmare I've had with the SAM, but that's for another day today. I've hogged it long enough. So thanks for letting me share. I hope that was helpful to somebody out there. But I'll say after that last talk, this really is going back to the Stone Age. But thanks anyway.
No, that's what it's all about. You can get. I imported some I2C 16-bit DACs from China, and they seem to work. They seem to work very well with the Raspberry Pi. Yeah, thanks for that. All very familiar. And Andrew, I think you have something that is kind of aligned.
Yes. Martin, just to pick up on one or two things, I did something very, very similar, only I put a beagle bone into the magnetometer box, popped the capes on beagle bones, which allows you to connect 5 volts to the I2C from the magnetometer and translates it to 3.3 volts, because I'm not clever enough to design something to do it. Flick the switch to 5 volts and it worked perfectly. So reading the data from the ADC on the magnetometer board worked a treat. My magnetometer lives outside, and my bugbear, what I wanted to understand was the way that it behaves as the temperature changes. It was quite obvious that it is affected by temperature. Now, can you see my screen? This isn't going to...
Yeah, that's working.
I'm not sure what you can see because it's... Zoom is a pain in the... Right, can you see that full screen, or is it still showing a...
No, that's good.
Okay, fine. Right. I wanted to understand how temperature changes affected the Eucra magnetometer. We've had some very hot days in the summer, and it was quite obviously it was being affected, perhaps not as dramatically as Fluxgate magnetometers, but no, it would be better to understand it. I'll skip that. I had the luxury of access to a warming box. My wife keeps bees, and beekeepers use a large heated box to warm their honey up when they're filtering it and jarring it up. It flows much better. So I popped the magnetometer in the shed, in the box, warmed it up over, and just played around with warming it up to sort of quite hot, sort of 38 degrees, which is the kind of temperature it was reaching on a very hot day when the ambient temperature in the garden was hitting sort of 28, 29. So what I found was I could warm it up from about 20 degrees to 38 degrees in about 30 minutes, and it was all nice and stable. The heating elements, to my surprise, didn't affect the output of the magnetometer. And by doing it over a short period, you're not, the Earth's magnetic field, unless you're unlucky, doesn't change very much. So these two graphs show the magnetometer sitting in the ambient conditions and the magnetometer sitting in the box. And as you can see, that the yellow line for temperature rises quite sharply. The magnetometer out in the garden, it stays nice and constant. And you can see there is a faint ripple on the A-axis, and the B-axis doesn't change very much. So the nice thing is Earth's magnetic field was nice and stable. So then plotting those graphs of temperature against output voltage, you get a very nice straight line. The first thing is that one axis is more affected by temperature than the other. That somewhat puzzles me because the circuits for each axis are practically identical. So is this a physical effect in the resistor? I don't know. I don't know quite why you should get different effects on each axis. Maybe I'll throw that over in your direction, Martin, as you were there when it was designed. I'll skip that one. So having got a nice slope, I applied the correction factor to some observations and data I'd taken earlier in the year. As you can see, this is the magnetometer out in the garden. Very big temperature change. Sorry, wrong way around. This is the one out in the garden during a hot day. Big temperature change, and you can see how everything moves up and down with temperature. Strip it out by data processing, and I've got a much nicer graph. I think I have completely misled you. That's the original data. And as you see, as temperature rises, it forces these outputs down. Here it is. It's nice and straightforward. It's a nice controlled way of understanding the temperature effects on a magnetometer. If you've not got the luxury of a big heated box, yeah, perhaps not so easy, but it's proving. I'm going to repeat this sometime on a nice cold day to see if cooling produces different results. But I'm quite happy that I've got an understanding of how the temperature correction works. So that was keeping me amused a little bit before Christmas.
Yeah, I too have noted a difference in temperature sensitivity between the two axes. And like you, I'm not really sure what's going on. Did Martin have any thoughts on that? You're mute.
Basically, this was you're looking back now, 17 years or something, like 60, 70 years ago. So the answer is probably no, I don't have any thoughts on it at all. The real credit for the design for the magnetometer really was John Cook, and he really did all the donkey work. His view at the time, because I did ask him about that, because I've been running a flux-gate magnetometer at that point for about five or 6 years, and I've been quite impressed with it. But the biggest problems I had with the sound design was the fact that it picked up a lot of noise. It used to take off the clock used to take it off, get noise on it. You mounted it more about 3 or 4 meters away from the controller. But the fluctuating magnetometer was really dreadful for the temperature. Now, John Cook, for the time, was very adamant that there was no temperature variation, but I would suspect that he hasn't done anything like the close work that you've done with it, so Andrew or Paul. I don't know. I must admit, I ran my UK RAA one for about 5 years with the old UK RA controller, those who remember it, and Starbase. But without sort of, I was never really quite happy with the direction Starbase was going. I thought it wasn't quite as flexible as I'd liked it to be from the front end, so I was quite keen to actually do my own thing anyway. But I never noticed any real problems with temperature variation. Having said that, I think, like you point out, the type of box may make a difference. My magnetometer at my old house and this house are actually located under a hedge, so they're actually kept away from bright sunlight. The size of a box is a very, very thick fiberglass box, which is fairly and bright white, so it's fairly well insulated anyway. I'm not saying it doesn't get warm inside, but it's not getting the heat going outwards. And the reason I know that is because the cat doesn't sit on top of it. And that's the first time an instrument goes on is that something is resting on top of it because it's nice and warm. So it's been out there for a couple of weeks, and the cat goes out most nights. And I thought if it's going to be warm, the cat would have attacked it by now, but it's been remarkably stable. So so it's definitely not getting warm at night, which suggests that it's fairly well insulated. So I don't know. I'm not saying it's not a problem, but I think having a look at the local environment may well be sort of the problem. I'm agreeing with you. It certainly looks like there is a minor temperature problem there, but nothing like a Fluxgate magnetometer.
It may just be the example I looked at. What I did was, like you, I wrote some bits of Python to read the I2C bus, log some data files, and then I've automated downloading those files once a day. I do, as you're describing, process them and pop the data up onto a website refreshes every 10 minutes. I could also, it's also with Python straightforward to write a bit of code to control the gain. So I had a little play with the turning the gain up. To be quite honest, or increasing the gain simply produced more noise for the period I tried it, rather than more sensitivity.
Sorry, yes, I don't know. I've got no more further answers really for you. I think the thing is just experiment until you get it as best you can.
Yep.
But I think, as I suspect, that looking at the shape of the graph, it looks like a fairly inverse linear correlation between temperature and the change that you're noting. So we should bring a temperature sensor in there. Would be a fairly quick way of actually removing any real problems. Yeah,
the temperature data there is taken from the temperature sensor on the magnetometer board.
Oh, so right. I forgot there was even a temperature sensor on it.
And again, a little bit of Python just reads that off and gets me a degrees centigrade directly. It was quite an interesting little bit of work to do. I've tried doing the same analysis using live data. The problem is, if you're using live data, the Earth's magnetic field is changing in the periods of time, over the length of time you're trying to observe a temperature change. So the fact I could actually warm it and cool it quite quickly overcame that little problem.
Thank you, Andrew.
Pleasure.
Does anybody have any questions for Andrew on this, or any insight even?
Or any answers?
Yeah, answers. Okay. Does anybody have any comments on anything else before we close?
Maybe Paul, I can share just two little things.
Please do, Wolfgang.
Let me see. I hope this is coming up.
Yeah.
Okay. I just want to pick up on one of the things that Alex said. I had to drop out for a moment, so when I came back, I noticed he had said something about outriggers. We are involved in an experiment, sort of outriggers, not quite the same thing, but what you can see here is our 25-meter dish focal point. So in the middle, you have the L-band receiver, the receiving horn for the L-band. It's a chaparral feed. and then offset to the side, you see two of these cloverleaf antennas, which Alex has mentioned, which are also used in the CHIME experiment. So these are actually the CHIME experiments antennas. And the idea of that is that we would simultaneously looking with CHIME at a certain part of the sky. Obviously, we only have a very small piece of the sky that we can observe with a single dish, but that is an experiment that we are involved in. And the main difficulty that we're facing with that is that our RFI situation in the frequency range from 400 to 800 megahertz is very, very severe. So we can only make use of a very small part of the spectrum. But this is an interesting thing, and hopefully eventually something will come out of it. The other thing completely different that I briefly wanted to show, let me stop sharing that and go to this one here. This is a completely different instrument, not our 25-meter dish, but it is a try to see a pulsar with our small 2.3-meter dish. And we tried it recently, early December, by taking our Pulsar Spectrometer from the 25-meter dish, moving it over to our 2.3-meter dish. And actually, we were successful observing the strongest pulsar. It was a little bit of luck because this pulsar has a high scintillation, and you sometimes see it, sometimes you don't see it, depending on the scintillation situation. So this is a detection of this pulsar with a fairly small instrument. The observation bandwidth was about 50 megahertz. You see 100 megahertz here full, because that's the bandwidth of our spectrometer. But since our RF filter on the 2.3-meter dish is narrow, it's about 50 megahertz, we only have signal in part of the spectrum. But it's sort of a nice experiment. There was one thing, though, which was not successful, and we don't understand why. So here we use our Pulsar Spectrometer, which we normally use on our 25-meter dish. And we thought, well, we could do the same thing using an SDR. We use Lime SDR, which has a similar bandwidth. We typically, with a Lime in Pulsar mode, we use 40 megahertz of bandwidth, but so far it was not successful. I don't know why. In principle, we should have seen the pulsar if we can see it with this spec end, but we didn't see it with a Lime. Anyway, I just show that as a sort of encouragement for people who want to do pulsar observation with small instruments. So if you're lucky with scintillation, it can actually be done. Yeah, that's, I guess, all I have for today.
Yep, thanks very much, Wolfgang. Any more for any more? Otherwise, we can conclude tonight. Okay, good night, ladies and gentlemen, and see you again next month. Good night.
Good night.
Good night. Goodbye.
Good night. Thank you.
Yeah.